Okay, so today we're gonna look at Kelvin temperature really quickly. And this is like the kind of final temperature scale that you'll ever really need. Now, obviously, on a day-to-day basis, we're used to using the Celsius scale. Certain areas in the world still use a Fahrenheit scale, which is its own thing. There's actually a few other temperature scales out there that are a little more obscure. If you're ever interested, you can go check it out. Seems like during the sort of like Renaissance age, or just after anyway, everybody was coming up with a different way of measuring temperature. So this is the Kelvin scale. It's like the SI final way of talking about temperature. Okay, so what makes it special? Well, first of all, let's just do a quick review of what temperature is. And what it is a measure, yeah, of the average kinetic energy in a substance. Okay. Now, that's easy to say, but what does it actually mean? Let's imagine that we have a tank here, and let's say, let's just deal with a gas, okay? So let's say that we have a gas in here. So we understand that matter is made up of particles, so these are particles of a gas. Let's just say it's oxygen gas, okay? So each one of these little particles represents one molecule of oxygen gas, all right? And they're all kind of, if we understand that they're a gas, zipping around, and they have little to no, in fact, they're an ideal gas, we assume they have no attraction to one another, okay? So you can just imagine a bunch of these little mini balls bouncing around in here like crazy, okay? Let's think about how the energy might be distributed amongst these atoms. So we'll actually, before we even do that, let's just say that this is at 20 degrees Celsius. Actually, you know what? I don't want to make it oxygen. I want to make it a different gas. I want to actually make it helium gas. Okay, helium gas. Okay, why helium? Well, helium is the lightest of the noble gases. So essentially, each one of these represents a helium atom. And helium atoms, if you recall from in chemistry class, kind of look like this. They have 2 protons in them, 2 neutrons, and 2 electrons in the outer shell. Okay, something that is small and that has full outer shells has very little attraction to other similar atoms. Okay, so helium is a special gas in that it has very little to no attraction to other atoms. It's very, very light, right? Okay, so that's why I want to do helium. It has a very, very, very low freezing point. Okay, because of that. Freezing, if you remember, is turning it. Well, actually, first it would be condensing to a liquid and then freezing to a solid. That happens at different temperatures, and that is based on the intermolecular forces, how attractive these molecules are to one another. Does that make sense? Okay, so here we have this tank. Let's think about how we might have the energies distributed if we consider all of the atoms together. And this is going to generate something that is called a Boltzmann curve. And what it essentially does is it's a statistical way of thinking about the atoms that are inside this situation here, okay? So over here, we're going to say that this axis is the number of atoms, right? Okay, so the number of atoms, if we have several billion, right, your scale would go up to several billion. And over here on the x-axis, we're going to have energy, so increasing amounts of energy, okay? When we say energy, we are really sort of, in this sense, referring to the kinetic energy of these guys, okay? And what you get is you'll get kind of a distribution that looks sort of like this. There'll still be some atoms that are moving very, very slowly, okay? And then there'll be a sort of a bulk of them that are around some average K. And you'll have this sort of tapering off, or some have actually very, very high energies. Okay, so in other words, it's not just that they all have the exact same EK in there, right? So when we're talking about what we mean by the average EK, what we'd have to do is we'd have to sort of look at, total number of atoms exists. Some have energy that's way up high, some have energy that's really low, but the bulk are sort of distributed around that kinetic energy. We say, okay, so somewhere around here, sort of if we look at this, is the average EK. Okay? So at 20 degrees, we might have a distribution like this, right? Now, what do you think is going to happen if we were to, well, first of all, let's imagine what a thermometer is going to do in this tank, right? So let's, we put it in there, the thermometer into the tank, and we find that the mercury in the thermometer kind of comes to that 20-degree temperature. Now, if this is the same temperature as the ambient heat in the room, it's all the same, right? Then the thermometer would already been at 20, and we would have just stuck it in there and noticed no difference whatsoever, okay? But let's say we just take the gas inside of here and we start to heat it up. Let's say we crank the temperature up to, I don't know, 100 degrees Celsius. Okay, think about what's going to happen with this distribution as we crank the temperature up, okay? Well, by cranking the temperature up, like, how are we going to do that? Like, what's a way that we could increase the temperature from 20 to 100? How might we do that? Sure, that's a great way to do it. You put it over top of a fire, and or put a Bunsen burner even underneath it, and we add heat in that way inside here. Okay, so as we add heat, that heat is going to, on the particle scale, start to increase the velocities of these molecules that are in here, these atoms that are in here, I should say, and they're going to go faster. Now, if you think about it, say I'm just heating up this little corner here, right? So what's going to be happening is, we have a chemical energy, release of chemical energy here, right? That's sort of heating up air molecules that are around it. Those air molecules are zipping and they're banking off the walls of the container, increasing the kinetic energy of the walls of the container. And then as these happen to bump into that area, they are then receiving some of that kinetic energy, and they're going to zing away faster than they came in, right? So by this method, as this happens, and then this is going to bump into another one, it's passed some energy, and by this sort of method, and that's a conductive or convection current type scenario, depending on how you want to think about it, we can increase the kinetic energy overall. But that doesn't mean that, for instance, this particular particle right here definitely has a higher kinetic energy. It might, okay? But the average overall will be an increase. So what we'll see as we increase temperature is we get kind of a more of a changing of the shape of this curve, okay? And so over here now is where our new average kinetic energy relies. There still is probably some very low energy molecules or atoms, but now there's just more that have that higher EK, okay? So our thermometer is going to be interacting with this system, these higher energy molecules or atoms, I keep saying molecules, these higher energy atoms, and they might be molecules, just depends. These higher energy atoms are now banking into the thermometer, and they're passing some of their EK into the actual mercury or alcohol that's inside the thermometer. That means that the particles making up the alcohol inside of here jiggle more, take up more space, and actually expand within the tube, and they move up. And that's what we're measuring as a higher temperature. Okay? Does that make sense? How much energy we put in is dependent on many different factors. Okay? How much energy it takes to move something from 20 to 100 degrees varies, right? It varies on the substance. In the case of helium, it's probably not going to take a whole heck of a lot of energy to increase the overall temperature, right? Volume, right? We talked about this last time. And actually, we can't really say volume. We should say mass, right? Mass is more important because we could have a very large volume with the gas, but very little mass if they're sparse, right? So essentially, though, how many atoms we have to increase the kinetic energy of is very important. So the mass that we have in here will also dictate the amount of energy that it takes to increase the temperature here. And that's sort of what we're going to talk to today in a little bit. Okay. All right. So last time we talked about how you would make a Celsius thermometer. But Celsius has like sort of certain drawbacks. I mean, it's great for everyday weather measuring and so on. We sort of tend to exist between, say, -40 and +120 Celsius, and everything sort of falls within that range. In terms of temperatures on Earth, I mean, there might be some times where or places where it might get colder or hotter, but in general, it falls nicely within that range. And people get used to using Celsius, and they wonder like, why would you ever need anything else? But what was noticed is that, okay, if we take that same box of helium gas, or even better, let's talk about something with changeable sides. Okay, so a balloon, say, right? We fill the balloon with helium gas. Okay, at 20 degrees Celsius. We'll get some volume. We'll call it volume X, right? And as we start to cool this down, we'll notice that the volume starts to shrink. Well, why does the volume shrink? It shrinks because the cooler we get, the less kinetic energy these particles have. And therefore, okay, so first let's think about what keeps a balloon expanded, actually, because that's kind of important. Pressure plays a role here, and we'll get into that in a little bit. But there's a pressure from the environment, right? There's air molecules smashing off the surface of the balloon. Basically, every time they hit, they're attempting to squash it down, right? They're pressing on it. And the gas inside is pressing back out. So we come to an equilibrium, right? Where, the gas banging off the inside wall and the gas banging off the outside wall equal one another, okay? If we, push more helium in, right, we'll expand the volume, right? Such that the overall internal pressure equalizes the outside pressure, right? A balloon's maybe not the best example because it also provides some constriction. I don't want to get too much into this right now, but this is kind of the scenario that's going on. Now, if we can decrease, right, we can decrease the temperature just inside of here, we would expect the balloon to start shrinking. And you've probably seen this. When you put a balloon in a fridge, it deflates and it looks all, flabby and deflated, right? So what's going on there? Well, let's say we drop it down to, -20 degrees Celsius, okay? Well, what's happening is these particles are moving slower, and therefore, on average, they're hitting the wall less, and they're hitting it with less kinetic energy, less, force if you want, right? They're just moving slower, okay? And therefore, it's not until you shrink the balloon down to a much smaller size, like, say, this big, okay, that there's enough collisions that it equalizes the outside pressure again. Does that make sense? Okay, and as you keep continually making it, colder, you have to, where the balloon will shrink and shrink and shrink so that this equalization process happens. There has to be enough collisions with the wall to equalize what's happening on the outside. The only way that can happen at colder temperatures is with a smaller volume. Does that make sense? Okay, so that's kind of the idea. By the way, if you think about it, this has lots of other applications, like a car tire, for instance. In the wintertime, car tires tend to have a little bit lower pressure, so you usually want to pump them up just a little bit when it's, -30 out or whatever, okay? And in the summertime, you got to watch that they don't heat up and, want to burst. I mean, they're probably not going to burst, but, it's not good to drive around with way overinflated tires. They don't contact the road properly or whatever. Okay, so if we were to graph this, though, okay, so we might have, let's just see here, how do we want to do this? We will put temperature on this plane, and we'll put volume over here, and it's noticed that there is a very linear relationship between volume and pressure. So this volume and temperature, There is actually a linear relationship between volume and pressure as well, but I don't want to go there just yet. Okay, so as we decrease temperature, okay, we notice that the volume of our gas starts to shrink down, right? And what you'll find is that that volume, if we can get to, I don't know, say minus 200 degrees Celsius in a lab or whatever, and then we extrapolate that, we can figure out that the volume will approach zero volume at a temperature of around minus 273 degrees Celsius. Okay? So what does that mean? What is the significance of reaching zero volume with our balloon? What must be happening, do you think? What's happening to the particles themselves as the volume shrinks to zero? Yeah, they're slowing. Right. So theoretically at this temperature, the motion of the particles stops. And if the particles have, so basically what we're saying is their kinetic energy equals zero. Okay? So the EK becomes zero. They stop moving. Okay? This is like a magic temperature in science, or in physics, I guess, that once you reach it, you no longer have the concept of heat anymore. There's no kinetic energy in the molecules. There's no heat. Okay? So another way of calling this is absolute zero. Okay? Absolute zero. The concept of temperature makes no sense below that. You can't get colder than that because stuff isn't moving anymore, so there is no heat at all. All right? It's kind of not an easy concept because we're not used to thinking about what does an complete absence of heat mean, right? Is minus 40 a complete absence of heat? Well, no, because the particles are still moving, right? There's still gas. The air has not frozen and become solid around us. We can still go outside and breathe. That must mean the particles of air are still moving, right? And thank goodness, if we got to absolute zero on Earth, we would have problems, right? If it was absolute zero, we wouldn't be able to breathe, right? The air would condense into a solid, all the air. And actually, oxygen, for instance, does freeze at higher than absolute zero. It doesn't mean it completely stops jiggling, but you wouldn't be able to breathe oxygen below its freezing point. And I don't know off the top of my head what that is, but I'm going to say it's like minus 200 or something like that. It becomes a liquid, right? But this is absolute zero. So the Kelvin temperature scale has some interesting properties. Kelvin temperature scale is, instead of being based on the freezing and boiling point of water, it's based on this sort of physics concept of the freezing point of any matter, or the point at which matter no longer contains kinetic energy. Molecules no longer contain kinetic energy. So 0 K is absolute zero. Okay? Now, the it's not degrees Kelvin either. We don't say degrees Kelvin. We just say 0 Kelvin. Kelvin is just like its own thing, like 100 newtons, right? It's not like 100 force newtons. We just say 100 K or 0 K. The actual degrees themselves in Kelvin, though, are identical in size to the Celsius degrees. So degrees of difference in Kelvin are equal to Celsius. So equal in magnitude to the size of a degree Celsius. So what we can do then is you can map from one temperature scale to the next, right? So if we think about it, let's say we have a Kelvin thermometer over here, and then we have a Celsius thermometer over here. Wow, it's not a very nice drawing, but whatever. Okay. So what that means is if my Kelvin thermometer reads 0 K, my Celsius thermometer would read negative 273 K. And there's actually some decimals on there, but whatever. Okay. We can cover. You can look up the actual, precise value to X number of decimal places in your book. This is close enough for now. Oh yeah. Sorry, man. Thank you. Good call. I was talking and not thinking. That is measured in Celsius. You're right. Celsius. Okay. So if we go up to 0 degrees Celsius, where are we on the Kelvin scale? 73 K. And let's say we go to room temperature, or let's say we go to 20 degrees C. What would we be at here? 293K. Okay, so you can map from one to the other. Um, should we write like a little formula to help us remember that? Or do you just want to leave it like that? Okay, we could. Degrees Celsius equals, what does it equal? Equals Kelvin plus 273, right? I guess that's our little formula there that should help us remember that. Okay, are there any more questions about that? Sweet.